Wow, look at that. So fancy.
Yeah.
That's a whole new world.
So why don't we try this out, Pamela? Go full screen. Let's see if this works. I'm going to put you on the spot. Now in the... Whoa. Okay. You mean business. So so can people hear me while this full screen Mike Brown tweet fest is up there?
Yeah.
Yeah. And can you hear, I don't know, like Moya?
Hello.
Just say hello for there. Okay. Were people able to hear Moya say hello there? All right. We can go back to us, but that was just a test, and that'll tell us if everything is going to work. Yeah, I think the chat. You're gonna ditch the chat, right? Yeah. So people are. I'm sure you're all wondering, how am I doing with my half of Canada being wiped off the map?
What? What?
Have you not heard about this?
I haven't heard about it. I'm on the other side of the world, man.
Yeah.
What?
Vancouver is not attached by road to any of the rest of Canada.
Yeah, so we had this like atmospheric river come through, and it was like a lance that just hit right through Victoria and Vancouver, and then went sort of a little further inland. And there was so much rain that the mountains, like a lot of the mountains, had mudslides from all the fires over the summer, which happened because of the heat wave over the summer, right? So we had the heat wave lead to the dead trees, which then everything caught on fire, and then everything was dead, and so we had mudslides. And so every rail line and every highway from Vancouver east has been cut off. And like badly, like, you know, like where there used to be a highway, now there is a 300-meter mudslide. So,
whoa.
Yeah, towns were cut off like all the way along this whole area. Like, you know, if you had rivers on both sides of you, which we all do all the time, everyone's, a whole bunch of towns were completely cut off, and they've been having to rescue people by boat and helicopter and stuff. Yeah, it's madness.
Wow.
Yeah, we have so far like one death, which is pretty amazing.
Wow.
Yeah, and so but the craziest part is like where I am on Vancouver Island, I was just north of this thing by about 20 kilometers. And so we had light rain. It was almost nothing. And yet 20 kilometers below us, it got heavy and started to have these crazy floods and absolutely devastating. It's a nightmare. Yeah. And so if we want to go anywhere, we have to go into the US, which fortunately we can finally do now because they opened up the border to the US like 2 weeks ago or like a week ago.
Yeah.
Wow.
Yeah. So you've just got
wild.
Yeah, you've got houses floating away, you've got cars, you've got a lot of animals, like a lot of livestock were like in barns that completely filled up. So it's pretty bad.
Wow.
Yeah.
Are they able to get supplies into Vancouver? Like, you know?
I mean, through the US. So we have to bring in and the rest of, we're the largest port for the rest of Canada, and so nobody can get any supplies to the rest of Canada. So yeah, this is bad. This is super bad.
Wow.
Yeah. Oh, I'm on the wrong audio.
Gotta remind me. Okay. Yeah. So anyway, and yeah. Sabrina Berger saying, I heard this affected the CHIME telescope. Yeah, CHIME is located in Penticton, which is hit really bad. So, yeah, astronomy is probably going to suffer from this as well. So anyway, yeah, that's what's happening here in Canada. I feel like all I do is just bring stories of disaster. Wait for the earthquake, because that's coming too, the big one. And of course,
the big one, yeah,
because we're supposed to get the big earthquake and then the big tsunami. So anyway, that's the
finally had a big earthquake in Taipei. I've been living over here for like a year, and we had like a 6.5. I don't know, maybe about a month ago. That one woke me up. Yeah. That was legit. I mean, just like small enough to like not make me really freak out, but it got my heart pumping.
Yeah, 6.5 is that's exciting. That's pretty thrilling.
For real.
Like, what was it like? Was your building shaking?
Oh yeah. Yeah, I mean, I was sitting in my bed actually, and then like I was like, yeah, I think, what am I supposed to do? Like, got up and stood in the doorway. Yeah, I mean, everything was fine, but yeah, it was quite a rattle.
It does seem a little ridiculous when you're told to stand in the doorway or go under a table when the whole building that you live in, the multi-towered building is just, multi-story tower is just shaking, creaking back and forth. You can hear the steel grinding inside the tower. Yeah.
Yeah.
So stop, drop, and roll.
Exactly. Yeah.
I've never experienced any of this. I've always lived on the East Coast. This sounds terrifying.
You have hurricanes, though. We don't have hurricanes.
Yes, we do.
Yeah. All right. Let's get this thing started. Hello and welcome to the Weekly Space Hangout for Wednesday, November 17th, 2021. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about looking for Planet 9 in older data. Earth's lower atmosphere is expanding. A diamond hauled from deep inside the Earth. And what is snuffing out galaxies before their time. All right. Joining me this week, again, all of the sort of everything is lost because everyone's just on the screen, and so it's obvious. So we got Dr. Alex Tichy. Alex.
How you doing? Good to see you.
Good to see you too. And for people who don't know, we got Alex coming on my show Friday. So in 2 days.
Right? Yeah, maybe. I have to look at my calendar.
It's in both of our calendars. I'll put it in my calendar. And and then Alex. And I think Alex is the last one of the people who are arrayed in front of you to actually show up to do an interview with me. So you'll be able to learn behind the scenes with Alex.
Awesome.
We've got Dr. Moya McTeer. Moya.
Hi, Fraser. How's it going? You already told us. Never mind. Forget I asked.
Yeah. I'm in a disaster-torn province once again. Right. And then we got Chris Carr. Hey, Chris.
Oh.
All right. With the best lighting of all of us. Pamela's jealous. And we've got Pamela behind the scenes. So at some point we can, if you hear me talking to someone and they're not answering, it looks like I'm talking to myself. I'm probably talking to Pamela. All right. So before we get into this week's news and special guests, I just want to give a special thank you to our good friends, fans, executive publishers, producers at the Weekly Space Hangout crew. They're an amazing community of people that you can join, talk about space, astronomy, and even summon guests to this show. So if you want to join this community, go to wshcrew.space, and they will hook you up and give you everything you need to know, ultimate power and authority. All right, so let's get on with this week's special guest. So we've got Dillon Dong. Dillon, welcome to the Weekly Space Hangout.
Hello. Thanks for having me.
Good question I always ask. Who are you? What do you do?
I'm a final year grad student, finally finishing up my Ph.D. I'm at CalTech currently, and yeah, I don't know what else you want to know about me. But...
well, what do you specialize in?
What do I specialize in? I specialize in sitting on the floor next to my two bunnies, writing papers currently.
Are they
Uh,
co-authors?
Wait, you have two
they're
bunnies?
most definitely co-authors in my heart. I do, yes.
Okay, I actually owned
Yes,
four
the
bunnies.
names are Eloise and Ruben.
Whoa.
You do.
Well, I did back in
We need to talk about this.
when I was a child. So, sorry to disrupt your flow, Fraser.
Well,
but
I know,
had
I
to-
This
know
is
it.
now the
I-
weekly bunny hangout.
I asked for this, Chris, at the beginning of the show. I said, feel free to jump in with any questions. So if you just want to turn this into a bunny conversation, I am down for that.
It's the weekly bunny hangout.
Bunny hangout.
Yeah.
So when you're not wrangling bunnies, what kinds of science are you working on?
I mostly work on finding slow radio transients in this large survey of the sky being done at the Very Large Array in New Mexico, called the Very Large Array Sky Survey. Very creative name, as astronomers want to do.
All right, so I got to ask, what is a slow radio transit?
Yeah, glad you asked. So a slow radio transient is basically a radio source that appears or disappears from the sky on not millisecond timescales, but maybe timescales of like months or years or maybe days. So basically, I look at radio images of the same part of the sky that were taken at different times, and I check to see whether all the sources are still there, or whether there are new ones that have popped up, or whether some of them have disappeared. Yeah.
What
And
types of
so it's-
sources are these?
So there's a lot of different kinds of sources. By far, the most common one, at least given the kinds of observations that I'm looking at, are flares from supermassive black holes. So actually, by far the most common radio sources in general, if you just put on your radio goggles and you look up in the sky, you'll see mostly supermassive black holes. But that's not what I focus on personally. What I focus on are various explosive phenomena that happen in galaxies that are actively forming stars. And so they're mostly supernovae that I look at.
And so what is the event that is causing how is a supernova generating radio waves?
Yeah, so a supernova typically generates radio waves through what's called a shock. And everybody listening to this podcast has encountered a shock at some point in their life. If you've ever driven on the highway and you've ever hit in a traffic jam, which I live in LA, this is like my day-to-day life.
There's nothing shocking about a
nothing shocking about it whatsoever. Yeah. So the analogy I like to use is that imagine you're driving along 70 miles an hour on the freeway, and all of a sudden you hit LA traffic and everybody in front of you is going 30 miles an hour, and you have to hit the brakes. Right? You suddenly decelerate. But what if you couldn't hit the brakes? Then you would crash into the car in front of you, and that car would crash into the car in front of it, right? And just create a chain reaction, right? And this dissipates lots of energy. Where you used to be going 70 miles an hour and you were storing lots of energy, you've basically sent it into all the cars that were in front of you. And this is what happens when the gut of a star that's blown up in a supernova crashes into the gas that's surrounding it. The guts basically slam right into that gas, and if the gas is dense enough, then it's like the supernova hit a brick wall. It basically just slows down to a crawl, and turns out that process is very efficient at producing radio waves.
And
So-
go
Sorry.
ahead.
Yeah, Dylan, just a question. I mean, emitting radio waves, this is obviously a very high energetic event. So are you seeing it in the radio because it's extremely redshifted? You're looking at very distant supernovae, or is it actually just producing a lot of radio waves?
Oh, it's actually just producing lots of radio waves. So the particular mechanism is your shock. This is something called first order Fermi acceleration, and it's like this whole thing that probably don't want to go into all the details on this podcast. But basically, imagine your shock crashing into like the ambient gas, electrons from that gas getting bounced around, and what happens is because there are also amplified magnetic fields in the shock, it can get trapped and get bounced back and forth. And each time it bounces, it gains more energy, the electron does. And then eventually the electrons stream out. And those electrons are actually moving very close to the speed of light. like more than 90% the speed of light. And when you have fast electrons moving in environments with strong magnetic fields, which you have both of those in a shock, then you produce luminous radio emission.
Huh, that's interesting. It's almost like, as you say, electrons moving through a magnetic field. That's sort of the similar way that you can, the way magnetism and electricity are interconnected. And so it's sort of the perfect conditions, I guess, to produce this kind of emission. Can you verify it in other wavelengths as well?
You can, yeah. So this particular supernova that I published in a recent paper had two complementary indications that it was a supernova crashing into basically a brick wall, right? One of them was the radio emission, which showed that it was a shock moving at only 1,000 kilometers per second, which is very slow for a supernova. And you also had optical emission that we measured via the hydrogen alpha line that also had basically the same velocity. So those are basically two sides of the same coin, telling you that there's something that is moving way too fast for it to be associated with the galaxy, but way too slow to be a normal supernova. And that happy medium is this supernova crashing into a brick wall.
So how can we use this to learn more about the supernova itself?
Yeah, so the really interesting thing about this is that most supernovae don't crash into brick walls. Most of them sort of just gradually sweep out the gas around them. They peter out really quickly, and then eventually, like, they get a little bit brighter as they sweep up more stuff. But in this case, something happened to create that brick wall, and that's what made the supernova special. Right? Something happened a few centuries before the star exploded that basically caused it to eruptively shed a huge part of its upper atmosphere. More than the mass of the sun was basically thrown out into this big wall of gas from the atmosphere of the star that had exploded. And that's really one of the things that set me on this journey to find out, why did we observe this kind of thing? Because why would you get this kind of eruption, timed so coincidentally with the supernova? And yeah,
what is your working theory then?
So my working theory is that there is a common cause to both the eruption and the supernova itself. And this is what I argued in my paper, which is that there is either a neutron star or a black hole that was in a close binary with a massive star. And this happens all the time. We see black holes in close binaries with massive stars, and we call them X-ray binaries in the Milky Way. The ones that we see in the Milky Way aren't quite close enough to actually spiral in, but if you have ones that are closer, then eventually they're going to undergo unstable mass transfer. The black hole or the neutron star is going to eventually make its way into the star itself. And so, it's a little bit hard to model what happens when this object enters the star. By a little bit hard, people have been trying to do this since the 70s, and they've made a lot of progress, but but there are still many outstanding questions. Right? And so this is the first time that we've seen one plunge in. And when it plunges in, it shoots out gas, creates this eruption, and eventually when it sinks its way into the core of the star, that we think causes an explosion.
Huh. Yeah. That's crazy. So what is the delay? I'm sort of imagining, so you've got this star with a black hole or a neutron star orbiting around it, or I guess it's orbiting the black hole or neutron star. I'm not sure who has more mass in the relationship. And I guess through mass loss, the orbit is changing and it's spiral inward, and eventually it actually enters the atmosphere of this star and starts causing mayhem, releasing this initial release of gas, and then I'm assuming it hits a ton of friction now, spirals down in and reaches the core. So how long of a time frame do you go from when it enters the atmosphere to when it actually ends up down in the core?
Yeah, so this is actually one of the $1 million questions here. And I think the most honest answer I can give is I'm not entirely sure. Going into this process, I thought, the time that it takes for the gas to make its way out to the radius that we saw like the brick wall at, right, is the time that it takes for the object, once it plunges in, to reach the core. But it turns out that theoretically this is very hard to produce. Typically, people argue that it should be, maybe tens of years at most, right? Whereas it took probably centuries for this brick wall to make its way out to where we saw it. One possible solution is that some of this gas may have been lost in the initial unstable mass transfer, and we know that lots of mass is lost in that phase. And so, it'll be interesting to keep monitoring this event and see whether, and also making better models of this kind of thing, to see whether we can really infer, which part of mass is lost during the initial mass transfer, which part was lost during the plunge-in, and so on.
Wait, Dillon, to counter that quickly, with your model that has a inspiraling black hole or neutron star, do you anticipate that there could be a co-signature with gravitational wave signal?
That's a really good question too. So my impression is it would produce gravitational waves, but it would be probably too faint to detect at any reasonable distance with current gravitational wave detectors.
And what would it leave behind?
It would probably leave behind.
I mean, obviously there'd be a black hole there. I mean,
yeah,
you can't get rid of that. But what would it do to the rest of the star?
Oh yeah, okay. So you would get a more massive black hole in the center, but the rest of the star is basically exploded outwards, right? And it's now this star guts that are just being blasted outwards into space, and a lot of the guts have now encountered this brick wall, and so it's going to be expanding a little bit slower than it normally would, but eventually it's going to create a supernova remnant. And the supernova remnant is probably going to have a really interesting shape to it as well.
And so could we find older examples of this, maybe in the Milky Way, with like telescope surveys? I mean, I think about some of the supernova remnants that we know of, Crab Nebula, the Veil Nebula, etc. Would one of these seem obvious if you saw it in a telescope?
We would have to be really lucky, I think, because these events are quite rare. So first of all, it would have to have happened in the Milky Way. In like a recent memory. Right? Probably the oldest supernova remnants we can see are like a few 10,000 years old. So it would have to happen within that time span. And
but
so,
if I showed you two pictures of two supernova remnants and one of them was this event, do you think you'd spot it? Do you think it would look obvious to you?
Ooh, not necessarily. So the signature that I would be looking for is something that wasn't like a sphere, wasn't a nice, didn't have nice spherical symmetry, because most of the mass that would have been lost in this process is basically ejected out in the plane of the binary, sort of in this spiral, as you can see in the artist's impression there. Eventually, the spiral merges, and the structure gets washed out on large scales, and probably creates some sort of donut shape. And so you would start off with this kind of donut, and then that donut would expand to larger and larger radii. More of the structure would get washed out, but then more structure might be created as it interacts with more of the gas that's outside, as instabilities develop. And so it's kind of hard to know what it would look like, but I imagine that the end product still wouldn't be spherical.
Right.
Yeah.
It's absolutely fascinating. What's next for your research?
Yeah.
If you can talk about it.
Absolutely. This supernova was found in a much more broad search. I wasn't looking for this kind of supernova specifically. This just happened to be like one of the most exciting ones I found. But I'm generally just looking for all sources that are appearing and disappearing from the sky, mostly appearing in the sky. And my mission is to try and find out what all these sources are. Right? And so there's a lot of really cool things that are out there. I've got another one which hopefully is going to get published in or get submitted in the next couple of weeks. That I think is probably an emerging pulsar and wind nebula buried at the center of a supernova. And we've got all sorts of cool things. Like I'm working with a student, and we're currently assembling a sample of all the different radio fluorescent stars that we can see in the Milky Way. I'm collaborating with a postdoc, and we're working on new jets that are being launched from supermassive black holes. Working with a grad student and professor on assembling a sample of stars getting ripped apart by supermassive black holes and what are called tidal disruption events. There's all sorts of stuff that we're going to be exploring. Yeah,
fantastic. So if people want to follow your work, where should they go?
I guess they can go to my website. I'll make an effort to actually update it, unlike many astronomers.
Yeah, that's
use a photo from like 15 years ago. Like the
yeah, exactly.
Are doing. You can be like 5.
There we go.
Yeah. Awesome.
Yeah.
Well, congratulations on the discovery and the work that you've done so far. And it sounds like a pretty exciting field. So please keep us posted. Now you're going to stick around for all that entails. So we'll have you comment on some of these other stories as we go. But thank you so much for taking the time to chat with us today. Really appreciate it. And again, good luck with your work.
Yeah,
we can talk about we'll talk about the bunnies next time, right?
Yeah, we'll set aside a whole show. If we find some more astronomers with bunnies, then light. All right. Okay, so let's start with Alex. You're on my screen. Found Planet 9?
No, you don't say. Yeah, so we're talking about Planet 9. For folks who have been living under a rock, we're sort of interested in this proposed potential 9th planet that astronomers, appropriately enough, have labeled Planet 9. The idea here, as a quick recap, is that when we look at these outer solar system objects, call them Kuiper belt objects, it's almost like a second asteroid belt out there, out beyond the orbit of Neptune. What these astronomers have found, particularly Konstantin Batygin and Mike Brown at CalTech as well, they see this sort of asymmetry in the orbits of these Kuiper belt objects, and they have inferred the presence of a massive planet out there about the mass of Neptune on an eccentric orbit, and very, very far out. We're talking hundreds of astronomical units out from the sun. They've proposed this, and they've been investigating this for the last several years. Now, this planet is, if it's out there, very far away, obviously very cold, and as a result, it's going to be very dim and therefore very hard to see in observation. So what people have been doing, Batygin and Brown, as well as others, have been, performing observations looking for Planet 9, as well as recently going back through archival data. And Batygin and Brown recently released a new paper. This was only about a few weeks ago, going through what's called the Zwicky Transient Facility, or ZTF for short, looking for Planet 9. And they have ruled out 56% of the area that they are searching. They have predictions for where this planet should be. And, they've done this real deep dive into the ZTF data and say, at least, a little over half of the sky we can now rule out as, it's likely that Planet 9 isn't there. So it still might be lurking out there. But of course, we haven't found it yet. And by the way, some people have cast doubt on the evidence for Planet 9. So some people think it's there, some people it's not there.
Planet 9,
what's that?
Well, there are certain people, pro Pluto people, who think calling it Planet 9 is already.
Yes,
awesome.
Clyde Tombaughl's grandson's bunny is still alive, and therefore we shouldn't be insulting Clyde Tombaugh's legacy by calling it Planet 9. So, to get to the present's work, this gentleman, Michael Rowan Robinson at the Imperial College London, has gone and done a deep dive on data from IRAS. Now, this is a really old data set, 1983, this infrared telescope. And by the way, infrared telescopes, what they're doing basically is looking for heat signatures. And as a result, you have to keep the telescope very, very cold. And so you have to have coolant on board, and that runs out. So these infrared missions tend to be very short-lived. It was less than a year for this mission, but it was really revolutionary. It surveyed the whole sky in the infrared. And actually, this paper is quite interesting because he worked, the author worked with IRAS data way back then, looking for, at the time, what they called Planet X. So there was this idea that there was a problem with Neptune's orbit, and they were looking for this other planet out beyond Neptune. Subsequent mass measurements of Neptune realized that there wasn't really a problem with Neptune's orbit after all, and therefore this search for Planet X, which was kind of in vogue in the 1980s, subsequently people were no longer looking for Planet X, kind of went out of style. But
I gotta say,
actually performed, and yeah.
Planet X brings me back to like all those old History Channel documentaries talking about like the mysterious Planet X. I just have to bring that up. Really nostalgic.
Yeah. Nostradamus and you know.
Yeah, it's like ancient aliens. Like, oh man.
Yeah, ancient aliens. I'm not saying it's Planet 9, but it's Planet 9.
This was a battle that we had to do in the science communicating. Well, it still happens, but like 2012 was a bad year for Planet X, Nibiru.
Right. Of course. Yeah, the Mayan prophecy. Let's mix it all in there.
Also, is that 250 million search results for Planet 9?
Yeah, probably something like that. Yeah. So what you're seeing on the screen is these recent news articles saying maybe we found Planet 9 in this IRAS data. So let's skip right ahead. He's done a deep dive into this IRAS data. This is a sky survey. What you're seeing there actually is Batygin and Brown's search through the ZTF data, but that's sort of a sense of where we're looking for it, right? They have predictions of where we're looking for this object. So you go through IRAS, and it's a sky survey. It's a huge amount of objects, obviously. So what they've done is gone through and tried to see, basically where are transients? Where do we detect something? And then subsequently, we can't find a match for it hours later or days later or weeks later or months later. That's more likely to be a moving object, right? And you can delineate between fast movers or medium movers or slow movers based on the time separation, or where you see an event and where you don't see an event. So the paper does a very deep dive looking for these objects and emerges with one object. It says, maybe this is Planet 9. The problem, though, is that it's not the same mass. It's not in the same location as where Planet 9 is expected to be based on the Batygin and Brown prediction. And so Mike Brown came along and tweeted, right after that paper came out, that's how it came across my attention in the first place, and said, well, it's interesting. It might be a real thing out there, maybe a real serendipitous discovery of something, but not really Planet 9, because IRAS is not really sensitive to the expected signal of Planet 9, and it's not in the same place. And he makes a very good point. Just because we find something out there in the outer solar system doesn't mean that's Planet 9. At least it's not what they have predicted. They make a very specific prediction. And so, you might find, there's lots of stuff out there. So if you find something else, that's really awesome in its own right, but it's not the Planet 9 that Batygin and Brown have predicted.
So do you know how many observations of this object they were, like, was it just one observation and then it was gone, or in the next survey of the data, or did they see a couple, did they see it move? Yeah, so it gets real technical in this paper, as you might imagine. They get the IRAS was in orbit around the Earth, so they observe it, and then they observe the same thing an hour later, but then when they come back the next time, they don't see it. This is, maybe weeks later. They don't get the weeks-long or the months-long observation, the confirmations there. It means it has moved. It's in the same place within an hour time scale, but on the order of weeks or months, it's no longer there, right? So ordinarily, they would reject those as saying, at the time, they're trying to map the sky. So they say, well, that's some sort of transient. We don't know what it is, so it goes on the reject
pile. So he goes into the reject pile, which is, of course, all this data is still available and worth working with. That's really what I think is so cool about this. We make these surveys decades after the fact. We're still getting useful science out of them. So you go into the reject pile and say, well, can we sort of cross-match these transient detections? And so that's what we're looking at here. We've got these 3 detections, and so you can kind of run the clock forward in time. Those spirals, by the way, have to do with the Earth's orbit. We're looking at a parallax effect right there. So you can see where they observed and kind of project where we ought to be looking for this object in 2021. Yeah.
And so, and so if we get one observation of this object moving through the field of view, or in the field of view and then gone, then it could have gone in any direction.
That's right.
In a circle, because you only had one. If you had 2 points, then you could know exactly where to look to find it today. But because it's there and then it's gone, and you don't even know how fast it's moving.
So right. So in this case, they do have a couple of different detections. That's what we're seeing in that plot there. Is that they saw it and they see something else that they associate with the same object. I mean, there's a good chance that it's the same object, but you don't know exactly for sure, right? As I think you're getting at, is that this thing pops up over here, this thing pops up over here. There's a good chance that they are associated, not 100%, right? And so then you can make a prediction and say we should sort of look in this, what he says, 2.5 to 4 degree annulus around the 1983 position, and maybe you will find something there. And again, maybe it's a real thing. It's not necessarily totally illusory, but probably not Planet 9.
Would you need to do so? I mean, I'm sort of imagining, say you took the Very Large Telescope and did a survey of that region in infrared, then that might do the trick. But 2 to 4 degrees, like a few times bigger than the moon. That's still a lot of telescope time, I think.
Yeah, I mean, depending on how wide your field of view is, of course, right? You want to do a deep drilling. And my understanding is that Batygin and Brown have been out at the telescopes in Hawaii, doing these sort of deep drillings of these fields where they expect it. And it's a big sky survey that they are carrying out just, to find Planet 9. So it's a big
really
job.
It feels like they're just trying to beat Vera Rubin. Like Vera Rubin is just going to, the 1 week later, they turned Vera Rubin. Yeah, they're going to beat Vera Rubin to the discovery. But yeah, like 1 week after Vera Rubin comes on, completes its first survey, done. There's all the planets in the outer solar system, all the asteroids, all the comets, they're all there. And so if Mike Brown and Batygin want any chance of getting this discovery nailed down, they've got to beat Vera Rubin to the punch.
They've got a few more years, right? I don't know when it's coming online, but I think that's right.
Next year.
Really? That's coming? Wow.
Yeah.
It's very exciting.
Yeah, we should see first light in 2022, and then it'll image the sky every 3 days.
Wow.
Dumping exabytes of data onto the internet.
Yeah.
Is that a real
it's going to be
number?
amazing.
That's a real number. Yeah, it's like a 1 followed by a ludicrous amount of zeros. That's awesome. Well, I wish everyone luck, but I place my faith in Vera Rubin, both the person and the telescope.
I think it's a good bet.
Yeah. All right. Thanks, Alex. Dr. McTeer.
Hello. I think in the interest of time and our comfort, I'm going to skip the depressing climate change story.
What?
and go right to the.
I was hoping you could explain
diamonds.
why my province is getting destroyed, but sure, that's fine.
No, it also wasn't a very satisfying story because basically the gist was the atmosphere is expanding. It's been expanding more quickly over the last 40 years, and it's almost definitely mostly because of humans. And we're not sure how it's going to affect weather, but we think that it probably means planes will have to fly higher to avoid turbulence in the troposphere.
Interesting.
Yes.
Huh.
So it can't explain anything about what's happening here, but neither can diamonds, although diamonds are less bad, usually. So let's talk about those instead. So this story is here to remind you that Earth is part of space, because it's a planet and planets are in space. Planets form from the material left over after stars form. So in a planet's early years, when it's still molten from all of the collisions of tiny little pebbles and protoplanets that make it, the heaviest materials sink down to the center. So you get this gradient in density as you go from the center out towards the surface of the planet. The immense pressure that you get inside the planet can combine elements into exciting structures that we don't get to see on the surface where temperatures and pressures aren't as high. And so this recently, scientists have discovered a new deep earth mineral that was hiding inside a diamond found in Botswana, and this diamond formed deep inside the Earth's mantle. The mineral is called Dave Mauite, after a prominent geophysicist, Ho Kwang Mao, who also went by the name Dave. And he is a well-known geophysicist who redefined our understanding of how materials behave under these high pressures and temperatures in the 70s by doing different experiments to see what will actually form under these different pressures. Dave Mauite, this new mineral, is a type of calcium silicate. It has a crystalline structure that breaks down into other minerals if it's exposed to lower pressure. So by the time it gets to the surface, it isn't Dave Mauite anymore. But the reason we made this discovery was because it was trapped in stasis inside this diamond, and they could use lasers to study the crystalline structure inside.
So there was a mineral inside it, like a diamond, like a fossil. Yeah. I'm thinking like amber, right?
Yeah, like a mosquito trapped in amber.
Right.
But it's minerals.
Cool. And so a diamond was like the only thing that could hold this thing together.
Yeah,
that's amazing.
I know, isn't it so cool? Just like happened to find this really cool mineral that for a long time we thought was there, but we couldn't find it because we couldn't get too deep enough in the mantle. But we think that Dave Mauite is important geochemically for Earth because it may contain traces of uranium and thorium, which produce heat when they decay. And the mantle needs a lot of heat to be produced so that we can keep the motion inside, the convection that gives us our magnetic field, and the motion of tectonic plates on top of that oozy mantle. So keeping it warm is a good thing for us. And this discovery is interesting because it shows that silicate minerals, this is a calcium silicate, can form deeper in the mantle than previously thought, and also that diamonds can form deeper in the mantle than we previously thought. So we're learning a lot with this new mineral discovery. And if we can find more of these high pressure minerals, then it might help us better understand the chemical composition of the mantle and how these elements and minerals get distributed in early processes of planet formation. So it does help us understand space to find diamonds in the mantle.
Well, it is interesting when you think about that the vast majority of the minerals, even water, is in the universe and is under these high pressure environments. It's
either deep inside planets or in stars, which are
right.
Yeah,
exactly. So it's not, you're not going to find, like, most of the water, say, is not going to be nice and sitting up on the surface. It's going to be under kilometers of intense pressure and temperature, forming weird exotic ices that are going to explain the magnetospheres and some of the other physics of these planets. And so to have a chance to dig up what is essentially the vast majority of the minerals in the Earth in the form that they're actually in is pretty exciting.
Yeah, I feel like they missed an opportunity. They could have made a Journey to the Center of the Earth reference with this article.
They didn't?
And they didn't.
Oh.
Yeah.
Yeah, that is pretty awesome. I wonder if there's more. Like,
yeah,
should people be slicing up more diamonds?
Well, they didn't have to cut it. It was lasers, so the diamond was not destroyed in the making of this research paper. And I think that this one was probably an especially deep diamond. I didn't dig into the origins of it, but the fact that we haven't found Dave Mauite before implies that it is hard to find on the surface.
Wait, so is that of the diamond or of the mineral?
That's the picture that was in the article, but I think it is the diamond. And then if you look closely, you'll see like black spots.
Yeah.
I think that might be the mineral.
Or
maybe it's just a picture of a dirty
stock, stock picture of a dirty diamond. Yeah,
who knows?
that's my. It looks too good. That's my instinct. It's got some creamy bouquet going on in the background there, so it doesn't feel like a science.
That's my band name, actually, Creamy Bouquet.
Creamy bouquet. Yeah, exactly. Very cool. All right, Chris.
Yeah, so I guess I'm up. The not yet doctor on the panel.
One day.
No,
One
I'm
day.
not a doctor either, so.
Oh yeah,
Yeah,
sure,
me neither.
sure.
So we outnumber them. We could take them.
Yeah, okay. So I'm here to talk about what's been snuffing out galaxies before their time, which was a great name for an article, by the way. Like, I wonder who came up with it.
we were talking about before the show that I so my job at Universe Today is to pick the titles for the stories, and then the writers all decide which stories they want to work on. But I've already pre-approved the title and the topic, and so that was the one. As I posted that to my Twitter feed, and I got a bunch of people going, just whining about my about my clickbait title. But anyway,
people whining on Twitter. I never heard of such a thing.
Yeah, I know. I felt so bad. Like, oh no, did I cross the line? Snuffing out galaxies? Is it too much anthropomorphization? But Chris,
I don't think you can ever anthropomorphize a galaxy too much.
100% agree, and I view that's my hill. So, all right, Chris, please tell us about the story. Tell us the science beyond the clickbait.
Yeah, so star formation is a pretty fundamental process that occurs in galaxies. So for the case of the Milky Way, for instance, the current pace at which the galaxy forms new stars is about 1 or 2 stars a year. So we call that the star formation rate, which is pretty standard across galaxies. For low-mass galaxies, the star formation rate's even lower. However, billions of years ago, the typical star formation rate for a galaxy like the Milky Way was significantly greater across the universe, where galaxies were forming 10 or 20 new stars a year. So that's an order of magnitude difference. And this transition in galaxies from this early, vibrant phase of intense star formation to this latter, more passive, quiescent period where star formation is largely suppressed is called quenching. And this question of what causes quenching in galaxies is actually one of the great long-standing mysteries for those who are interested in understanding how galaxies form and evolve, like myself. And so there's this new effort that's trying to address this challenge called the Verticio survey, which is actually an acronym for the Virgo Environment Traced by Carbon Monoxide survey. And this work is led by Toby Brown, a research fellow at the National Research Council of Canada. So go them. And the survey is...
Yeah. Go Canada.
Go Canada.
Blame Canada. Yeah.
Yeah, they produced a good one. And so this survey is dedicated to observing about 51 galaxies in the nearest galaxy cluster, which is the Virgo cluster, which is about 60 million light years away, using radio observations from ALMA to detect the cold molecular gas of these galaxies, because that's sort of the fuel you need for subsequent star formation. So the goal of observing clusters of galaxies rather than just individual galaxies is that you really get to see this process of quenching in the most extreme galactic environments imaginable. And actually, the picture you're seeing right now of the Virgo cluster was taken by Chris Mijos, who was actually my advisor back in undergrad. So it was quite sentimental seeing that photo.
So what, I guess, is the process? I mean, what is the addition with this new paper to the search for this explanation?
Right. So the Verticio survey really serves as a really high resolution data set that sort of allows you to watch this process of quenching in real time. Because what makes the Virgo cluster an interesting choice for a survey like this is that, unlike many other galaxy clusters, many of the galaxies in Virgo are still star forming and have sizable gas reservoirs, while clusters are usually like the graveyards of galaxies, flowing with these massive red quenched galaxies that died long ago. But in Virgo, the hope is that you get to see the process of death as it happens, and like see those quenching processes like as they occur. And so we're quite lucky that Virgo is so close to us that we're able to have like this excellent data set of seeing in action the quenching of galaxies.
But I mean, as you said, right, the Virgo cluster is our big close cluster, and so we're not looking that far back in time, say 50 million years plus, as opposed to the billions of years when the galactic party was actually happening with star formation. So is that a representative sample of a like, isn't that just like a more modern era for a galaxy?
So the thinking would be that the processes that are going on in Virgo now, that the quenching processes that we'll be able to see in high resolution in Virgo, would be representative of the same processes that must have happened at high redshift to many other clusters who by this point are all red and dead. So the actual process of quenching can be caused by both internal and external processes within the galaxy. So for like a low mass galaxy, the internal process that can result in quenching is feedback from the death of massive stars. So when they detonate as supernovae, they can sweep up the surrounding gas and sort of lift it out of the galaxy in the form of these like large scale galactic outflows. While in more massive galaxies, in addition to the supernova feedback that's occurring, you can also have black hole feedback as well. So as gas funnels towards the center of the galaxy, it can sort of excite an energetic response from the supermassive black hole, which blows out the gas from the galaxy. Where clusters becomes more interesting is that you get to see these external mechanisms in process as they happen, because all these galaxies are so close to one another, and they're all sort of messing with one another, and he's passing by all these tidal interactions. The gas supply can be stripped in these interactions. And another situation is called ram pressure stripping, where you have these galaxies moving through the hot intercluster medium, and so the intercluster medium kind of acts like as a wind as you're moving through it, and that hot wind is able to strip the cold gas off the galaxy as it passes through that hot medium. So there are a lot of different processes going on here, and they're all occurring on their own unique timescales. And so resolving all of this madness is one of the great aims of the Verticio survey, because it provides like such a great data set for folks like me to really dig into.
And so you don't get, like, if you just had a single galaxy all on its own far away from a cluster, it wouldn't experience this kind of quenching.
So conceivably, the internal processes that are involved with quenching, like from supernova or black hole feedback, would be the prominent modes of how you could quench the galaxy in long time scales. But yep.
Oh, and so then, like, this survey will help you try to break apart those two variables. Which galaxies are clearly mostly getting affected by their internal processes, and which ones are interacting and getting stripped in ways by their partners. I know you can get situations where one galaxy can just blast another galaxy with its supermassive black hole, with its quasar, right?
Yeah, because all these processes are happening on different timescales as well. So the quenching caused by tidal interactions may be successful in only a handful of millions of years, while quenching from other processes through supernova feedback or black hole feedback may take billions of years to actually succeed.
Would it be assumed that the Milky Way went through that at some time in its history, or is going through it right now?
So the interesting case of the Milky Way is that the star formation that we're seeing may actually be slightly above what you would expect for a galaxy like the Milky Way, because we have these two dwarf galaxies nearby, like the Large Magellanic Cloud and the Small Magellanic Cloud, which have like their own sizable gas reservoirs, and there actually is evidence that very recently these, like through these processes that I mentioned earlier, that some of the gas is actually being stripped from these near satellites and feeding the star formation going on in the Milky Way, which could actually delay the process of quenching that you would expect for a galaxy like the Milky Way, because we have that extra reserve supply pouring in.
Fifth Dimension is asking in the chat, does dark matter quench galaxies? I mean, dark matter is the dominating matter in the region. Would that play a role in it, do you think?
Could it quench the galaxies?
Yeah. I mean, it doesn't interact in any way, shape, or form except for gravity, but it sure brings a lot of gravity to the party.
Yeah, I guess in a way, the galaxy interactions are primarily dominated by the dark matter. So, like for instance, if two massive halos are passing by one another, then the gravitational interaction there could be enough to maybe cause some stripping of the host galaxies within those halos. So, but it's an interesting question, though.
Yeah.
So the dark matter should help a galaxy not quench.
Oh yeah, because it would deepen the potential well and thus make it harder for the galaxy to escape.
Yeah.
Ooh. Yeah.
Interesting. And so this is this kind of a survey. Astronomers can just keep going back to the well as they have new ideas. They can look at all of this data and try to come to some conclusions.
Yeah, like
I love surveys.
Yeah, that was the aim of it. Like they wanted this survey to be like the Gaia of galaxy quenching, like this big, like high resolution data set that theorists and data statisticians can all to answer their questions.
Yeah. I think surveys are a total game changer. And obviously, Vera Rubin guy, as you said, like just collect everything and then let people look for whatever they want, as opposed to having to book telescope time to scan something. So, absolutely interesting. Fascinating stuff. All right, we've reached the end of our hour, so I want to give my co-hosts a chance to shamelessly self-promote what they're working on. Dillon, you stuck around for the show, so you get to go first. Is there anything that you want people to check out, people to learn more? Some bunny site that you are a fan of?
Yeah, I mean, check out your local rabbit rescue. Bunnies are very misunderstood pets, but they're very loving, and you can bond with them really nicely. Like every time I walk up the stairs now, Eloise and Ruben stick their little noses out the balcony, and they're like, "Do you have bananas for me?" And usually the answer is no, and then they get upset with me, and they turn their backs to me, and they're like, "I got no words for you." No banana, no love.
I didn't know rabbits could eat bananas.
They're very cute. Yeah. Like bananas are the rabbit treat. Like I've never met a rabbit that does not like bananas.
True.
Fun fact of the day.
All right, Alex. Thanks. All right, Alex.
Exomoons all the time, and I think I've mentioned on this show before, but what I'm interested in right now is microlensing. Microlensing has the potential to reveal very low mass objects in our galaxy, and that includes exomoons. So I'm really sort of jazzed up about this angle for looking for these things.
I double checked. We're talking on Monday evening.
Yeah,
so
Monday,
right after my live show on Monday night, we're gonna have a chat. So for people,
yeah, I'm looking forward to it.
The open space, they can follow that. So there you go. All right,
yep.
Moya, what are you working on?
I am working on my podcast. It's Exolore, EXOLORE. I did a show about the world building of Stargate earlier this month, and the first part of that is coming out tomorrow. So check that out, and you can find me on Twitter. I'm GoAstroMo.
Fantastic, Chris.
You can follow me on Twitter at @TheRealCCar. Right now, I'm writing my a host of papers that I hope to actually put out soon. So, but as the life of a grad student.
Yeah, that's how you get the doctor.
Yeah.
Gotta publish or perish. All right, of course, Universe Today. Come check out all the things, including interesting news articles. Like, actually, Alan Boyle one of the best space journalists I know is working on an article for us right now about the Starship plans. Elon Musk just announced all of his plans for Starship 2022, and we should hear the schedule. And so that story will be on Universe Today momentarily, written by the best space journalist I know. So pretty excited. All right. Well, thank you, everyone, for joining us this week. Thanks to all of my co-hosts and our special guests who stuck around for the whole ride. Appreciate that. Thanks to everyone watching us, both on YouTube and on Twitch, if you're there. And thanks to all the moderators, as well as special thanks to Nancy Graziano and Pamela behind the scenes engineering the show. We really appreciate you helping out and sticking around. Thank you, Pamela. All right. We'll see all of you next week. Thanks, everyone.
See y'all.